Hello everybody, welcome back to our channel. In this video we're going to be solving a Physics 7B momentum practice problem. As usual, if you're finding this content useful, please make sure to leave a like and subscribe. It helps the channel a lot. So the problem statement goes as follows. Please feel free to pause the video in order to try this out by yourself or just follow along. So in space we have an object, a big object, which is initially at rest, and the object is 10 kilograms total. And it basically explodes for whatever reason into three pieces. A 3 kilogram piece which is going west, a 3 kilogram piece which is going 45 degrees north of east, and we don't really get any information about what happened to the third piece. So the questions that we have to follow is, first of all, we need a complete momentum chart, then we need to figure out what the speed and direction of the third piece is, and then just an extra question about the forces that all of the objects are feeling. So as you can see, I've written all of the relevant information here on my notes. So I have the total mass 1, mass 2, and I don't really have mass 3. And I do have the final velocities of pieces 1 and 2, but again, I don't really have any information about piece 3 at all. So let's just go ahead and start it. Let's just answer this, in order, starting with the momentum chart. So first of all, the instructions are very clear in that this object is initially at rest, and at rest means, not moving at all. So when all of these pieces are together, none of them are moving. That basically means that the initial velocity of 1, 2, and 3 is equal to 0 because they are stuck together, which means that they have the same velocity, and furthermore, they are at rest, so nobody is moving. Now, momentum is equal to mass times velocity, so because nothing is moving, then we can just say that no one has any initial momentum at all. And because the rules of a momentum chart are that all of the rows and all of the columns have to add up, then adding this up is going to give us an initial total momentum of 0. So there we go. Now we have one column. That's very good. The next thing that we can do is figure out this part right here. This part right here, remember, is reserved for external forces or external impulse that our system is feeling. In this particular problem, we are in space, which means that we don't have any external forces like gravity or friction or anything like that going on. That's the beauty of space. That is why so many of these problems are in space, actually. So because we don't have any external forces, that means that we can pretty much say that momentum is conserved, and that means that we get to put a 0 in here. Now again, the rules of a momentum chart are that all of the columns have to add up and all of the rows have to add up, which means that this is a 0. So there we go. So that is the initial information, and then we just basically complete it based on the fact that we are in space. So now we actually have to calculate some numbers. We do have some masses and some velocities to work with. First of all, even though we were not explicitly told what the mass of the third asteroid is, we were given masses 1 and 2 and the total mass, which means that we can very easily figure out what this mass is. So it's just gonna be a mass of 4 kilograms. So we have 3, 6, 10 kilograms total. Now we can also figure out what the final momentum is for the first and the second asteroids, because we do have their masses and velocities. So let's just go ahead and do that. The first thing that I'm gonna do, however, is just change this into actual vector form. That is going to be more useful. So B final 1, we have 10 meters per second going west. West is the x-axis, and west actually means negative. So in vector form, this is just negative 10 and then 0 meters per second. Now the second one is not going to be as straightforward because this is 6 meters per second. Oh, north of east, I'm sorry. So north of east, 45-degree angle, and this is 6. However, if you do know your SOHCAHTOA, and hopefully you do at this point, then you know that we can just use this angle over here. So this is just going to be 6 cosine of 45, 6 sine of 45. So just putting that on a calculator is going to give us 6 cosine of 45, 4.24, and 6 sine of 45 is going to be the same. Yes, 4.24. Now both of these are actually positive because this is north of east. So that means a little bit east and a little bit north. That means plus and plus. So this is our final velocity in terms of x and y components. So now that we have this, we just need to multiply times the masses in order to get the actual momentum, because remember, this is a momentum chart. We can't just put velocities here, it has to be momentum. So I'm just gonna go ahead and do that. So final for 2 is just m2b final 2. So this is negative 10 times 3, so this is just negative 30, and then 0 times 3, that's just gonna be 0. And then p final for the, oh, this is the first asteroid, I am so sorry, there we go. And then for the second asteroid, this is mass 2, bf2, and this is going to be equal to 3 times 4.24, 3 times 4.24, so times 3, 12.72. So 12.7, let's just cut it at, well, let's just 72, 12.72 kilograms meters per second. So now that we have this information, let's just go ahead and put it on our momentum chart. Negative 30 and 0 is just an arrow going, so this is 1, yes, it's just an arrow going, you know, left. And 12.72 is just an arrow going northeast. You know, the scale is already going to be a little bit iffy, but whatever. So 12.72, 12.72. There we go. Perfect. So now that we have this information, we basically have everything that we need in order to figure out all of these spaces right here. So let's just go ahead and do this in order. So because we start at 0 over here and all of the rows have to add up, then 0 plus something has to be equal to this. So then basically what goes here is exactly what we have over here so that it can add up. So I'm just going to go ahead and copy the exact same vectors. Like this. And now in order to figure out what goes here and here, that is very easy because I just need to add up my vectors. Well, let's just remember that it is this plus this has to be equal to 0. This plus this has to be equal to 0. So I just need to be mindful of that, and then I just have to figure out this plus what is equal to 0 basically. So what I'm just gonna go ahead and do that. So let's see. So this is gonna be 30 minus 12.72. So this is gonna be 17.28. And then 0 plus this is equal to 0. So this is just gonna be negative 12.72. There we go. And then over here, we're just gonna have the exact same situation. There we go. And this is a little bit to the east and a little bit down. So this is just gonna be, you know, an arrow, a little bit east and a little bit down. Yeah, negative. So this is just gonna be this. And as you can see, all of the columns add up and then all of the rows add up. So this momentum chart is well done. This plus this is equal to 0. 0 plus 12 minus 12 is equal to 0. So everything adds up. So we basically just finished this part of the problem. This is a complete momentum chart. As you can see, we have the arrows and they are pointing, you know, in the right direction. We do have our x and y components, so that is why I'm not super careful about keeping my magnitudes relative to each other, because when you have the actual numbers, then you know, that is of course telling you more information than just grabbing a ruler and just being very picky about like every single inch and centimeter. But anyway, so let's just move on to part number 2, which is what is the final velocity of the third asteroid. So let's just go ahead and figure that out. So I have my final momentum for the third asteroid, and I have the mass for the third asteroid. So this is actually going to be very straightforward, because if I just concentrate on this part right here, P final 3 is equal to mass 3 B final 3, right? So in order to get B final 3, which is what we want, we just need to divide B final divided by the mass. So this is just gonna be 17.28 divided by, what's the mass of 3? Oh, it's 4 kilograms, here it is. And negative 12.72 divided by 4. So B final for 3 is going to be equal to 17.28 divided by 4, that is going to be 4.32, and 12.72 divided by 4, that is going to be equal to negative 3.18. Like this. Perfect. So now that we have this figured out, we basically just need to, yeah, so this is final answer for part number 2. So now we just have to figure out for part 3. So part 3 is basically saying, so let's just create, you know, some space. If delta T of the explosion is equal to 0.1 seconds for all of the pieces, who felt the greater force? So for this part right here, we basically want to go back and remember our equation for delta P, because the equation for delta P is the one that relates delta T to delta P. So the equation goes delta P is equal to the net force times delta T, right? So now this problem is saying delta T is exactly the same for all of the asteroids. Given this information, who felt the greatest F? And as you can tell by just looking at the equation, whomever has the greatest delta P is going to have the greatest net force, right? Because F net is just equal delta P over delta T. So in order to figure out who felt the greater force, we basically have to figure out who felt the greater delta P. And how are we going to do this? Well, we do have our delta P's in components, but this is essentially speaking about the magnitude. So all I have to do is turn this into figure out the magnitude of these 3 vectors, and whomever has the greatest magnitude is going to be, you know, the right answer to this problem. So the magnitude of the first delta P is actually just 30, because we just have one component. So if I use my Pythagoras theorem, that's just going to be 30 Newton seconds. The magnitude of the second one, I need to use my Pythagoras theorem. This is just going to be 12.72 squared plus 12.72 squared. And let's just figure that number out really fast. 12.72 squared plus 12.72 squared, close parentheses, give me the square root, 17.98. So far out of the first asteroid and the second asteroid, these felt the greater force, but let's just do the third one. So this is just going to be 17.28 squared plus 12.72 squared. So let's just go ahead and do that. 17.28 squared plus 12.72 squared, close parentheses, square root of that is going to be equal to 21.45 Newton seconds. So the right answer is that as the piece 1 felt the greatest net force due to the explosion, because experience the highest change in momentum. Final answer. So this is going to be a final answer, and this basically finishes our problem. So I hope this this video was useful to you guys. I hope you follow along. Again, if you're liking these problems, leave a like on this video, and I'll see you guys on the next video. Bye bye.